This first example is great to illustrate a couple of points. So first of all, to look at the triangle proportionality theorem, I can compare 4 and 2 to 6 and 3 because I can do part to part. Say 4 over 2 is at the same proportion as 6 over 3. Those both reduce to 2 over 1. And so I can see that the proportionality is true. If, however, I want to look at 8 and 12, at first glance you can see that 8 and 12 are not going to reduce to a 2-to-1 relationship the way that 4 and 2 do. And that is because 8 and 12 are corresponding parts of the triangles. They are the bases of these overlapping triangles. So if I want to write a proportion including 8 and 12, I would say 8 corresponds to 12. At the same rate, this is the base, its side and its whole side, which is 6, as 4 and 6 compare, at the same rate as 6 and its whole side of 9 compare. These all reduce nicely to 2/3. So just a nice illustration to be sure when you are comparing, make sure you have corresponding pieces. Using a part compared to a part or a part compared to a whole is legitimate, but these bases need to be compared to the complete triangles. These next two examples are fairly quick and straightforward. 12 is going to compare to x at the same rate as 10 will compare to 15 because those lines are parallel. That is the triangle proportionality theorem. And so when we cross multiply, we have 10x is equal to 180. And so x ends up being 18. Nothing too earth-shattering about that. The next example, though, does require you to pause. In this case, it appears when we have 4 and 6, you want to look over here. We do not have triangle proportionality in this example. What we have to look at instead in this example are those overlapping triangles because x and 20 represent the bases of those two similar overlapping triangles. So when I go to write my proportion, I'm going to compare 6 and 10 to the entire side, which is 10 and 20, to be sure that I'm making a fair comparison. So I'm going to say 6 over 10 will have the same proportion as x over 20. So I did side, short side over the entire side, small triangle over large triangle, small triangle over large triangle. When I cross multiply, 120 is equal to 10x. We find out that x is 12. This example, while it looks initially complicated, is actually, again, very straightforward. You just have to remember some small notation items from geometry. We clearly have parallel lines cutting transversal, so we have proportional parts. When you look at those proportional parts, we have two variables. So when we dig a little deeper in this picture, we see these hash marks, which tells us that these two segments happen to be equal. And if those two segments are equal, these two segments are equal. So this actually turns into a very straightforward algebra solving problem to solve for x. If I add 2x to both sides, I end up with 5x. If I add 4 to both sides, I end up with 10. X is 2. When I go to solve for y, I have 5/3 y plus 1 is equal to 3y. And even though I love fractions, the easiest way to deal with this fraction is if I multiply everything by 3 to clear that fraction. go ahead and do the distributive property. When I take 3 times 5/3 y, the 3's will cancel and leave me 5y. When I take 3 times 1, I'm left with 3, and that will equal 9y. Subtract 5y from both sides. 3 is equal to 4y. Divide by y, or divide by 4 to get y alone, and I end up with 3/4 is equal to y. And that's just a nice review of how to deal with fractions. So tune in to the last video for the similar right triangle theorem.